In this video, we're solving DeepML problem 15, linear regression using gradient descent. To solve this problem, first we need to understand what linear regression is. Basically, the goal is to fit a straight line to our data. So if these are our points and we want to predict y from x, maybe revenue from the number of sales, for example, we would want something like this. Technically, the relationship here is affine since it has an intercept, but it's still called linear regression. Now, this is a simple example since there's only one input feature. But maybe instead we want to predict revenue from the number of TV sales, computer sales, and printer sales. Then it would look something like this. This is also possible, but in a multivariate case, it's usually easier to write it using linear algebra notation. I'm not going to teach linear algebra in this video, but I might explain more in other videos covering linear algebra topics. Instead of writing our data as a list of points, we write one input matrix called X, where each row contains all the input features for that data point. Then we also have Y, which is a vector where every value in Y is the associated output value from each row in X, like revenue in our example. Then the model equation looks like this instead. People also often add a column of ones to the matrix so that the first weight takes on the role of the bias or y-intercept. Then our goal is to find the slopes or weights and the y-intercept for our function so that it matches our data as closely as possible. There are multiple ways to do this. For linear regression, it is actually possible to jump directly to the correct answer, but if you have too much data, that can be computationally quite expensive. So the approach in this problem is to use gradient descent. To do gradient descent, first we need a way to estimate how good our current weights are. We can use the mean squared error loss to do this. It measures the squared difference between each prediction and ground truth label, so that the mean of all of these square differences is always a positive value. The goal then is to find the weights that minimize this loss, which means that the predictions are as close as we can get them to the ground truth labels. To do this, we take the derivative of the loss, which is pretty straightforward for MSE loss. We can also write it in matrix form, like this, which is easier to implement in code. This is called the gradient. The second part of gradient descent, the descent part, starts by computing the gradient based on our data and current weights. Because we have the gradient of the loss, it tells us the direction we need to move the weights in to increase the loss as quickly as possible. However, since we want to minimize the loss, we instead move in the opposite direction. That's why it's called gradient descent. We also use a parameter alpha, also called the learning rate, to decide how fast we want to move in that direction. A large alpha means that it will move quickly, but might overshoot the minimum. A small alpha might move much more slowly, but it is less likely to miss that minimum. If we go back to DeepML to implement this, you can see that they were nice enough to give us the X matrix with the column of ones already added. We'll make sure to store the data shape for later when we'll need it. Next, you want to reshape Y to be a column vector so that all of our matrix operations will go as expected. We will also initialize empty weights for our model, one for each column in X. Now, gradient descent is an algorithm that has to be run repeatedly, and we'll hopefully converge on the correct result. So we are given a number of iterations to run it as well. For each iteration, we will do the same thing. First, we will run our model on the data. Then we will compute the error between the prediction and ground truth for each prediction. We then compute the gradient, which is now pretty straightforward to do. And finally, we update the weights by moving in the opposite direction of the gradient. After all of the iterations, you return the final weights. Here you can see that we flatten them for DeepML's auto testing since we had the weights as a column vector for better compatibility with matrix operations. Let's run the test case first. And since that passed, let's submit, and all tests pass. This is a pretty introductory example of gradient descent, but when we get to neural networks, things start to get more interesting. Anyway, hope you enjoyed the video.